You can read it. It says it is impossible to find explicit formula. What they mean by explicit formula here is the elementary function. We talked about this representability, sine and cosine and those things, and antiderivatives type of thing. And if you can't write down antiderivative or elementary function, and what was the last resort? Anybody remember? The last way to represent a function which is a lot bigger than elementary function. P word? Power series, that's right, power series. We have that. What was the disadvantage of a power series? It's not usually defined everywhere. It's usually defined in a small interval called radius of convergence. In that case, what can we do? Of course, that's something we're going to do, and you can find this chapter quite later part in the book, but they want to sketch the solution a little bit so that you feel a little bit better than, oh, I can't solve it. Like that. So before we do that, they also emphasize, if you see this type of first equation, left-hand side derivative, right? Right-hand side, x is the main variable, y is the unknown function, not differentiated, right? What is this f? Is a function, not operator. This f is an algorithm, what you do to the two numbers, not to the functions. So we treat it as x and y as a number, so x plus y, but right-hand side cannot be x plus y prime, right? This will be a function operator. So this will be just this type of basic arithmetic, and this is allowed too. This is something you can do to the two numbers. That's what the right-hand side is. So if you have like this, most of the time the polynomial, if f is an elementary function on two variables, then they're saying it always has a solution. It's a powerful statement. Okay, you will see some examples and you will understand why it exists. Solution always exists. In general, it requires some heavy theory. But that's a big theory here. The solution like this, when f is an elementary function, for example, then this always have a solution. Okay? And we want to sketch one of them. Here's an example, and I will just use this example so that we feel much better than, you know, y prime is f of xy. That's too abstract. So I look at this one, and I hope you see that's fit into that. This is what you do with the two number x and y. Multiply y squared. There's no functional operation there. It's just arithmetic. So that's example of that. Okay. If you use Wolfram Alpha and Mathematica, it's not going to give you the answer that is something that you recognize. It's just they couldn't solve it, so named it weird. So this is really not representable. Even with a power series, it's going to take a long time to find a solution. So what can we do? We approximate, right? So what can we do with approximation? If a function is given, this is what you learn in Calc 2. If you can't really handle it, if the integral is hard or something, then you consider this thing here, right? What is this called? F of x equals that. It's a Taylor series, right? So I'm using the word series. Series is infinite terms, right? So is this left-hand side f of x is the abstractly, you know, function we're looking at. Right-hand side is analyzed like this. Is this an approximation? Or is it actually exactly equal? It's not. If you have dot dot dot, it's precisely equal. So you have to understand the meaning of dot dot dot. Dot 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 means is you add all, you know, what happened eventually. You can't really do that eventual part. You can only think about that eventual part. That's so it is exact. But if you truncate it like this, you stop at the first term, then it's approximation, right? Then you can write like this. F of x is good, and this approximation is go really bad if you're far away from C, right? You have to be very close to C. And in the graph, most of the time, this is line, right? This is a number, this is a slope, and this is a main variable. So this is a line. So most of the function is not line. So this is actually very bad approximation. If you want to do a little bit better, then you have to throw in one more term so that it's curved, right? Quadratic, so you can do a little bit better and things like that. All right, this is what we can do. If the function is there, and if we have to, like, initial value problem at C, let's say that was something. I give you a number like 0 or 2. I think I chose y of 0 equals -2 in the next example, so I'll throw in this type of problem. All right. If I start from there, what is a solution? We expect there's a unique solution, not only there is a solution. So we're going to use this idea to kind of to see how this function they describe looks like, right? So this idea makes sense? Look at x equals 0. Let's see, let me sketch it roughly in here. X equals 0, y is negative 2 there, right? The function passes through that, right? We want to figure out how this function y, described by differential equation, looks like around that point x equals 0 down to negative 2. And this one will tell you how it looks like the tangent line, and this one will tell you how the quadratic approximation looks like. If you go further, how the cubic approximation looked like. If you actually sketch them together near x equals c, they're quite similar to each other. But if you go away from x equals 0, they're very different. But as you throw in more and more term, suppose you get better and better, and sometimes it doesn't even close. And if you fall to the right, in that case, the radius of convergence is small. All right. So here is your first exercise, already challenging. I haven't really taught you anything to do, or but here's a theory that I reviewed from Calculus 2. And then I'm asking you to do this. Exercise number 1. Here's the same differential equation you see there, right? Y prime equals 1 plus y squared. And y of 0 is negative 2. So here, function passes through that, right? Fair enough? We don't know what that function is, but we know it's approximation t1x, right? Probably you can do that. So here, y equals f of x is a solution to this. What does this IVP stand for? Anybody? Initial value problem. Does it look like initial value problem to you? Differential equation, I gave you one data for the first order. That's the initial value problem. Okay? Without this initial value condition, there may be infinitely many solutions. With this one, there's only one solution to that. It is called initial value not because x equals 0. Any one piece of data given is called initial value problem. What is t1x at 0? Okay? Where did 0 come from? In the Taylor series. In the Taylor series Taylor polynomial description, what is the z correspondent here in the letter? By looking at the 0 here, what is 0 then in this context? C is 0, right? C is 0. That's the central point. We're looking at x equals 0, c, x equals 0 there, to the right or left, small neighborhood. How is the function approximated? By t1. Okay, so you already know what C is there, right? C is 0, C is 0, and C is 0. What you have to figure out is f of 0 and f prime of 0. If you figure those two out, and you have an answer for t1x, and that's going to be tangent line. Don't you think t1 is going to be the tangent line, right? That's going to be the tangent line. All right? So what is the task? Here's a solution. Compute what and what? F of 0, right? And f prime of 0. You figure that out. Then you come back here and simply state this polynomial. That's your exercise number 1. All right, was that okay? What is y of 0 or f of 0? That's the function. If you think about it here, y equals f of x, right? That's the function. So y0 is f of 0, and it's given. That's a part of the given condition. So that part's easy. Y prime of 0, then it's f prime of 0, right? That's the same thing. So if you look at the differential equation, y prime of 0 is when you plug in x equals 0 here. So x is 0. That's what you get there. This one, y is a function. If you plug in x equals 0 there, this should be the correct notation, y of 0, right? That's given there, right? Negative 2. Therefore, negative 2 squared. But it's multiplied by 0, so 0 anyway. But if this one, 0, like x equals 1, then this will be negative 2 squared, right? It's going to be there. So I got this derivative value to be 1. So that's the Taylor series, Taylor polynomial of degree 1. Okay? What was the geometric meaning of this Taylor polynomial again? That's analytic. But what geometrically, what does that mean? What kind of line? It's a tangent line, right? So here's a tangent line. Here's a negative 2, slope 1. Is that right? I wouldn't stretch too far because it's not a good approximation as you go. So tiny bar here. If you look at the graph around that x equals 0, it looks just like that. I don't know if it is above or below, but it looks like that, right? Fair enough? That's T1. Here's even harder challenge here. Can you calculate T2? We know this part, right? We figured out, you can see that first two terms already part of T2. All you have to figure out is this one, right? So can you figure out f double prime of 0? Then you have quadratic approximation, right? And that'll tell you even better shape of this unknown function now. So that's your exercise number 2. I'm going to keep it there. Exercise number 2. What is T2 of x at 0? I'm showing you what T2 is. That's a quadratic approximation in analytic term, and also called Taylor polynomial of degree 2 at x equals 0. C is the same. Again, the first two terms of T2 is already figure out T1, right? There's one more term, and all you have to figure out is what is f double prime of 0. This is what's given. Y prime equals 1 plus x times y squared. Y0 is negative 2. Can I compute y double prime, right? That's what it's asking. Yes, question? Yeah. Writing y prime, that's Hope this solution makes sense. It's all about y double prime. So here's the equation. You can just differentiate one more time. Then you get this one in here. So I had to use a product rule. And y is a function of x. So when you differentiate y, you have to use a chain rule, right? So when you differentiate y squared here, it's a 2 times y to the first. Then you have to multiply the base of that one. Think about how you differentiate sine x whole thing squared, right? You multiply cosine x at the end, and that's what that is. So value of y double prime 0 is plug in x equals 0 there. So that this means a 0, there's nothing there. It's 1 times y 0 squared. Here is a 2 times x, that's 0. And you plug in x equals 0 there, so that's y 0. Plug in x equals 0 there, and that's y prime 0. Okay, so y 0 is negative 2, that's a part of the problem. And in the earlier part, we compute y prime 0 being 1. So we know everything in here. Turns out to 4. 4 is not the coefficient of this one. You have to divide it by 2 factorial. Remember that Taylor series thing? Yeah. So this is the quadratic polynomial. So if you actually sketch the solution of this function, whatever that is, it looks like this one is a quadratic. Now you can go one more. You can differentiate one more time. Where is our here, right? You can differentiate one more time, then you have a triple. You can differentiate one more time. It gets more and more complicated, but you can see, you can compute it, right? If somebody pays you to do it, and you'll do it. You can compute that value and come back here and throw in more and more points. Then it becomes a better and better shape. There's a solution, right? Obviously, this computing this many more and more term to go to farther and farther to the right is a lot of irregular computation, right? Differentiating this one many times is actually really complicated. With even Mathematica will have trouble with if you reach 5 and 6. So how can we actually sketch a solution that extends far to the right or left? Realize that this is too complicated. So the next idea is that T1 was a simple, so why don't we stick to that T1 and we'll do something about it, and that's the direction field. But this is a good place to introduce the idea of approximation connected to the Taylor series. We'll come back to that eventually, so I introduce it a little bit. So what is the direction field? Just deal with the T1. T1 was easy, right? You didn't have to differentiate anything. The differential equation itself, let me go back to our original one, 1 plus x times y squared. It always tells you what the derivative is, so it was really easy. The idea is that go to that xy plane, you grid points, right? You plot those points and sketch the tiny segment there with the correct slope. That's their idea, right? So here's an example. Here's our same equation, okay? So this is what I'm going to do. And I'm going to look at x between negative 2 and positive 2. Just a random choice. I chose it here. And then I divide those by delta 1. So you hit all the integer coefficients. If it is a 0.5, you will go with negative 0.2, 1.5, negative 1.5, like that. So I divide that, and then I'm going to show you how that one looks like. Hope this picture makes sense. These are the coordinates that is described in that first bullet item. Does that make sense? X starts from negative 2 to positive 2, increased by 1. So negative 2, negative 1, 0, 1, 2. Is that right? Y coordinate starts from negative 2, increased by 1, negative 2, negative 1, 0, 1, 2. This creates this point. If I choose each of this point and try to sketch T1, tiny T1x at each of this point, we repeat those procedure. What is it we just did? Which point was it? Anybody remember which point it was? 0, 0, negative 2. So it's down there, right? What was the slope? Was y prime to 1. So I'm going to sketch it like this. Fair enough? That's the tangent line looks like. So let me go up there. So here is y prime, the slope, right? That's the meaning of y prime. It's 1 plus y squared, x times y squared. If I go up there, this is where y of 0, this is x coordinate 0, right? And y coordinate there, what is the y0 value there? Negative 1. Right, if I try that, what is the slope there? slope is this formula, right? What is it? 1 again, because this x is still 0. X is still 0, so no matter what, this is going to be always 1. You figure that out? Here's always, everywhere is 1, right? If you find a solution that passes through that point, locally that looks like that. Right, let's go over here. Look at that. What is that value there? X equals 1, right? How about y? 0. So what would that be? 1 again. 1, 0 still makes 1. If I go up there, x equals 1, your initial y value is 1 here this time, right? So 1, 1. So what do you get, the slope? 1, 1 plus 2. So 2 is going to be a little bit higher there like that, right? Slope 2. How about here? How about here? I'm sorry. 1 comma 2, right? So 1 comma 2. So the slope here is 1, 4. Did I get this right? Yeah, x equals 1. It's just 5. So 5 would be like this. Fair enough? Now it's a tedious procedure. You go all around and put this tick mark everywhere. Alright? So I did it with this computer software. So that's if you diligently do those, go through that, and then you have this idea. Alright, we were here, right? We were here at the beginning at x equals 0 and y equals negative 2. That's where we start, right? What is it suggesting? It is the curve looks like this. No idea how it looks like in between, so probably it's not true, but I'm just going to go straight like that until I reach x equals 1. Did you have a question, Stephanie? Yeah, reach there. Now it's suggested once you reach here, the slope must be like this, right? So I'm going to go like that. Once you reach there, the slopes, oh, you have to go like this. This is really rugged picture. It's actually smooth and beautiful. And if you go backward like that, so, and then once you reach there, it says you have to turn around like this. So maybe I'm going to go from here like that, and like that. It's really bad, right? So I did it more with a computer, and throw in more points in between. Computer can do all this easily. So the tedious calculation done by army of electrons. Alright, it's done here. It's x equals 0, negative 2 there, right? Then I'm going to follow this line. This is follow the crowd. You know what? Follow the crowd? Yeah. It's just follow this line. Wherever they're going in your neighborhood, you have to just follow that. And that seems like a solution to what equation? Y prime equals 1 plus xy squared. If you start at x equals 0, at the y equals negative 2, that seems like shape of the solution. You find this one in line with that quadratic approximation we calculated t2x. Fair enough? What is this thing called? Direction field. This is what it's called. Direction field. Alright, so I just sketched the solution of that one. And this whole marks here with the lines, they are called direction field. Right? Does that make sense? You'll be asked to do this much in the test. Roughly sketch it like this. Right? Not this. I made this short script in the Mathematica. So if you type in the right hand side of the differential equation, B is the bounding box, and this is a number of arrows you want to put in between, and use this D field, and it's going to sketch what I showed you before. So welcome to use it. This is called solution. It's not direction field. It's actually the solutions that said in Mathematica. Use those direction field, nicely sketch the actual solution in here. So if you start from x equals negative 2, that was here. X equals negative 2. And if you follow this line, it's not direction field. They actually sketched it for us, so that you can see the solution set is nicely sketched. If you go to x equals 0, y equals, if you started there, where that is where x equals 0, y equals 0, right? If you started there, and that's the solution they're suggesting. That's the solution set. So that is called integral curves. That's the official name for that. It's one of the, you sketch all the solutions. Alright, so you can use that if you like using that kind of technology. It's just there. Alright, this is your work, exercise number 2 or 3? 3. Sketch the direction field of this first order equation y prime equals x plus y. And go ahead and create the same box, -2 to 2, -2 to 2, with a division 1. So you will have that 25 points again. And first thing I want you to do is the first one, and then we're going to compare the answer. Sketch the direction field. Go to each of the 25 points and put that little mark with the correct slope, right? That's the direction field. The second part is asking about x equals -2 and y equals 1. So try to sketch around that neighborhood first. Sorry, I'm not giving you enough time, but I hope you got some of the things that sketches in it. For example, -2 comma 1 is up there, -2 there. And what is the slope? -1, right? Because you add this 2 coordinate, -2, y coordinate 1, and you get -1, and slope is -1. So this is a shape of a line with slope -1, right? And if you go around, it looks like this. Okay? Once you get a couple points correct, then you know it's just tedious precision, you will get it right. So this direction field looks like this. Any question? That answers first item? So let's do the second item together. I started here, right? And it's suggesting you go, straight direction there, right? You can see why I chose that point. You arrive at here, what does it say? This direction field. Yeah, keep going, and it says keep going like that and keep going like this. Yeah, it seems like that's a solution. And in the case, that looks like a straight line, right? Straight line. So can that ever the one straight line be a solution to this differential equation that comes to you, right? So why don't we try that? Can I try this one? Y equals mx plus n. Isn't that how all the straight line looks like? Is it possible this one satisfies this equation, right? Okay, let's try it. Like that exercise number 6 in the book. What do? You differentiate this one, right? That's m. That's the left-hand side. The right-hand side, this is left-hand side of the differential equation. What is the right-hand side? X plus y, right? So what is y here? mx plus n. Isn't that right? So these two, if this is a solution to this differential equation, left-hand side of the slope m must be the right-hand side, which is 1 plus mx plus n. Is that right? This should be satisfied. Right-hand side is a function, right? How can this be a constant function? Only when m equals -1. If it is -1, x disappears, it becomes a constant function, right? So if left-hand side as a function is a constant function, right-hand side should be a constant function as well. So right now it's linear, then it makes this one should be m equals -1, so it's a 0, right? So we have a function y equals -x plus n, then it must satisfy this one there. Also, not only that, this particular 0 and this m and n must be equal to each other, and that's another thing, right? So that should be have no choice, but y equals -x and m equals 1, n must be this one. If there's ever straight line that satisfies this differential equation, it had no choice, it must be this one. Okay? But there's one more condition, which is this initial condition, right? It's just lucky if you plug in -2 there, it becomes a positive one, right? Therefore, it happened to satisfy this condition. So we just proved that y equals -x minus 1 is a solution to this differential equation, satisfying this initial condition. So we discover that by looking at this direction field, and mathematically rigorously proved that this, the linear function, happened to be the solution to this differential equation. Fair enough? Question? So this from here is not solution, is a little remark or observation coming out of looking at this direction field. So here is better picture there to fit in. Now just write it here. This is more refined direction field, and there is, I think, the line there, y equals negative x minus 1. Got any question about direction field in general? Well, yeah, it's not quadratic, but you can kind of follow using T2, but I'm not sure if a quadratic solution actually works. I don't think it's quadratic. It is exponential probably. Yeah, high order, right, but not polynomial. Yeah, because it suggests there's curvy in there. Might have sketched that. It might not. Oh, here, there's a straight line. And here's some curvy solution there. Right. Also, I keep it in here.